Guys, Mrs. Grayback again, here to go into our next lesson, which is part of the new material that Miss Bertolasini and I are going over about ions and ionic bonding. Now, there's really two different types of bonding when it comes to elements. And remember, when I talk about bonding, what I mean is all those chemical formulas. So if you actually just did a quick Google search for chemical formula, right? And let's just see what pops up. So if I look at these general images for chemical formulas, what we're really seeing here are how different things combine together. So for instance, here we have the chemical formula for water. We have two hydrogens, okay, two hydrogen atoms, or H2, and one oxygen atom, O. So therefore, its formula looks like H2O. That 2, that subscript, meaning that there's two hydrogen and there's only one oxygen. I could look at 100 other chemical formulas that are out there. For instance, let's take a look at this one. Okay, this is a reaction involving a compound called methane. Here we have oxygen and then carbon dioxide and water. And in this situation, we have a lot of different chemical formulas here. Okay, we have CH4, so that 4 applies to this hydrogen, but not to this carbon. So there's actually an imaginary 1 next to that carbon that we're not seeing, which we don't need to see, because it's just like any kind of exponent, sorry, not exponent, coefficient you see in a algebra problem, right? If you just see x, it's assumed that there's one x. So these are chemical formulas, okay? And if you just Google search chemical formula, you're going to see a whole bunch of those. So elements, a lot of the times, don't exist in those singular atomic structures. They're usually bonded to something else. And there's two different ways they can do that. One is through ionic bonding, and then there's another called covalent bonding, which we're going to get to in another video. So when we talk about ionic bonds, okay, the key word there are ions. So let's take a look at this quick little video that kind of talks about this bonding process.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
So that's a pretty explosive reaction that we're seeing. And what I really want you to take away from that video is that we have two separate atoms there, or sorry, not atoms, two separate elements, right, in groups of atoms. So we have billions of sodium atoms in that small little chunk of metal, and we have billions of chlorine atoms in that cloud of chlorine gas. And the two of those things are combining together to make something completely different called sodium chloride. So both sodium and chlorine are actually extremely dangerous by themselves. Sodium by itself will explode when it comes into contact with water. We saw that before we left, before we took this hiatus, we saw that all those metals, when they come into contact with water in group 1, have this violent reaction with water. And so you can imagine if you ingest it with your body being made mostly of water, like what that would do to your body. Chlorine is another poisonous gas. If you breathe it in, it could really do you some serious harm. However, when we take these two and we bond a sodium atom to a chlorine atom, you're getting table salt. Sodium chloride is table salt. We sprinkle it on our fries. We use it in food all the time. It's probably sitting on your kitchen table or your dining room table at home just waiting to be used for tonight's dinner. So when you bond elements together, you're completely changing the structure and the function and the properties of those elements. Okay, and when elements combine together, we call those new substances compounds. So this is an element, this is an element, this is a compound. One sodium and one chlorine bonded together makes sodium chloride. But why do they do this? Why do elements want to bond together? Why aren't they happy just being by themselves? And to really understand that, we have to get into something called the octet rule. Sometimes it's also called the rule of 8. And what that means is that elements want a full outer shell. Think back to our last lesson when we talked about how we have those valence electrons. So here we have that sodium atom with its one singular valence electron, and chlorine's got 7 valence electrons. Okay? And when we look at these two atoms, neither of its outer shells are full. And atoms want to be full. They want their outer shell to have all 8 of those electrons. The only exception to that are things like helium, hydrogen, lithium, and beryllium, or elements 1 through 4. So if you go to your dynamic periodic table, so ptable, right, .com, that was that dynamic periodic table that we've been using. Okay, so if we look at those first 4, so hydrogen, helium, lithium, and beryllium, okay, all of those, when we look at their Bohr models, they only have those 2 outer rings, and it's actually that first ring can be full with 2 valence electrons. So in that situation, when we look at those 4 elements, we're not worried about getting 8, but those 4 are the only exception. Everything else, everything past beryllium here, so boron, carbon, nitrogen, oxygen, fluorine, neon, all the way through these, want to have those 8 valence electrons in their outer shell. They want to be full. They want to be, sometimes it's called being fat and happy. Elements want to be fat and happy. So the way that elements do this, the way that sodium gets that full outer shell, is it is going to lose this electron. Okay, it's going to lose that electron, and by losing that electron, you can see that if we get rid of it, this outer shell is full. So if we get rid of this ring altogether, then the next shell is fat and happy. Okay, on the other side, chlorine, however, is going to want to gain electrons, because it's easier for that chlorine atom, instead of getting rid of all 7 of these, that sounds like a lot of work, getting rid of all 7 of those. So instead, it just wants to gain 1. And if it gains 1 electron, well, that means that this outer ring is fat and happy. And the important thing to remember here is that when we gain electrons, you're making a negative ion because you have more negatives than you do positives. And when you lose electrons, that means you now have more positive because of those protons in the nucleus. Remember, there are protons in here. So if I lose an electron, I'm unbalancing the number of negative charges and positive charges, so I'm no longer a neutral atom. I now have a charge. So for instance, your lithium, okay? Lithium is going to want to either gain 7 electrons here, which is a lot of work, or it could just lose this one. And if it loses this one, its outermost shell is full, because its outermost shell is that first ring. It can only hold 2 electrons. You know, it's like when you stack smaller glasses inside bigger glasses. This small glass can only hold 2 electrons. So it's full. It's up to the brim in electrons. So if it loses this electron here, that means it loses this ring, which means that its outermost ring is full. Chlorine, if it gains an electron, its outermost ring is full. So it really comes down to, is it easier for the atom to gain electrons, meaning it becomes negative, or is it going to lose electrons and therefore become positive? So when this happens, when you're gaining or losing those electrons, you're forming ions. So usually those electrons that are lost by positive forming ions like sodium are going to be gained by the electrons that want to have them. So for instance, here we have sodium and chlorine. So when we look at their Bohr models here, You can see that by getting rid of that one single electron, you're getting rid of this ring entirely, which means that this electron is coming over to the chlorine atom, and by doing that, we have filled in the outer shell of chlorine, and we have gotten rid of the ring for sodium. And by losing the electron for sodium, this is now a positive atom, because now we have more protons, more positives, than electrons, or negatives. So we have a positive ion. And chlorine is the opposite. Now chlorine has more of these electrons than it does protons, and therefore is a negatively charged ion. And using Lewis dot structures really help us kind of point out what types of elements would bond with one another. So here we have a very simple idea of sodium giving its electron to chlorine. And that's what bonds them together, because when you have oppositely charged particles, it's just like the north and south pole of a magnet. When you get opposite charges, they're going to attract one another, sticking them together. So we have that, the positive coming into contact with the negative there. And that's what's bonding this sodium atom to this chlorine atom. So why is this useful to be able to use these Lewis dot structures? Well, if we can predict the number of electrons an element needs to gain or lose for that full outer shell, we can then figure out what types of compounds are going to form together. So looking at sodium and chlorine, we've talked about this one. They form an ionic bond because sodium is giving the electron it needs to get rid of to chlorine. So this has no more electrons surrounding it, so its outer shell is full. And this one has all 8. So the quick rule to remember here is that if you have 3 or less dots in your Lewis dot structure, then you want to get rid of all those dots and give them to something else. If you have 5 or more dots, you're going to want to gain electrons so you look like chlorine right now, like this chlorine, where you have all 8 electrons surrounding it. This is fat and happy, and this one is also fat and happy, but it's gotten rid of that Lewis dot structure, or it's gotten rid of that one valence electron in its Lewis dot structure. So here we have another example of magnesium. So magnesium is in group 2, and because it's in group 2, it has 2 valence electrons in its outermost shell. So that's why we see in its Lewis dot structure 2 dots. Oxygen only has 6 dots. So if we look at oxygen, oxygen is in group 16. So when we look at the charge that oxygen is going to form, it wants to gain 2 more electrons in order to fill its outermost shell. So by gaining magnesium's 2 electrons, we have filled oxygen shell, while at the same time making magnesium happy because it's gotten rid of those 2 electrons. So by doing that, these 2 are going to bond together to make MgO. Its chemical formula will be MgO, or magnesium oxide. And that 2 plus is going to cancel out that 2 minus. Now, it's not always a 1-to-1 ratio. So here we can see magnesium, we only need 1 to cancel out 1 oxygen. For sodium and chlorine, we only need 1 sodium to cancel out 1 chlorine. But sometimes you get a situation where you get something like calcium and chlorine. Calcium forms a charge of 2 plus because by getting rid of these 2 electrons, we now have lost 2 electrons, so we have 2 more protons than electrons, so this gets a positive 2 charge. Chlorine, on the other hand, is going to gain. So 1 electron is going to go to this chlorine, and the other electron is going to go to this chlorine as well. And by doing that, we're going to cancel this out. So its chemical formula would be CaCl2. Now, I'm going to show you how to do this in a little bit more detail in the next video. Somebody very handsome, you don't see his face in the video, but he's a very good-looking individual, and I think that he has a lot to teach you, is going to go ahead and show up in this video here to kind of walk you through an example problem with magnesium and chlorine. And please, 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 if you're having a hard time with the ionic bonding problems, come to office hours on Tuesday. The link is in Google Classroom. I will be there to answer questions, and I'll be happy to help you out. So let me know if you have any issues, and hopefully I will see your smiling face then. Okay? Stay happy, stay healthy, everybody, and I hope that you try and enjoy the time that you have at home.